efficient matrix, but it doesn't tell you anything about the solutions to a linear system. So you need the constants to show up somehow. And if you have an augmented matrix, you actually put the constants in. And if you have a matrix equation AX equals B, then you would do like A inverse B, and that's how the constants would show up, right? So if you want a solution, you have to have the constants show up in there somewhere. Okay, cool. All right, so very much we're kind of like leaving, here, let me get the polls going here. All right, so we're very much leaving behind linear algebra, and we're going to start on the next stuff pretty quick here. And in order to do that, we need to talk a little bit about sets and how we can work with sets. So yeah, we're going to start off with this question, and let's see if you can do this. Sure, yeah, grip or tap. Yeah, I can do that. Okay, now out of curiosity as well, you know, I know that some people would have done this sort of stuff in high school. You can, you know, I'm not going to say who didn't do it in high school, but who did do this in high school, like unions and intersections and set differences and stuff. Because I know some people did it. Okay, have not. Okay, somewhat. So for those of you who did it, did you do these Cartesian products, which is this like times thing? No? Okay, so that one's kind of new, right? Did you do set difference, like subtraction? No? Okay. So unions and intersections probably aren't too crazy, but we are going to have stuff to talk about when it comes to set differences and Cartesian products. Right? And the reason that we're going to talk about this, so we're going to start talking about counting and discrete probability and things like this. We're very much going to leave linear algebra behind, and it is actually possible to talk about linear algebra in the context of these things. And there's tons of cool applications when you start to merge these. But yeah, we're going to be working with sets and needing to intersect them and union and all these sorts of things. So we need to know what these things mean and how we're going to use them. Okay. Interesting answers so far. Very interesting answers. Okay, I'm gonna give you 30 seconds. Get your answers in. Curly brackets, square brackets, and round brackets. So usually curly brackets, Brandon, this is actually a really good question. So curly brackets usually are indicating, you're indicating the elements of a set itself. The square brackets are usually reserved when you're talking about intervals. And in this case, like in this question, you might be like, well, what are these round brackets, right? The parentheses. They just say that we use them exactly the same way that we would use them in, like, if we were doing addition and subtraction. We're trying to say we're going to take the union, like look at answer C, for example. We're going to say we're going to take the union first, and then we're going to subtract from that union the set 836, right? Whereas if I didn't have those parentheses there, it might be a little bit ambiguous. Am I taking 6,35 and then unioning it with 636 minus 836, right? Like, what is the order of operations? So, you know, when we use brackets in algebra, we use them to enclose the orders of operations. In this context, that is what that means as well, right? So we're using it to separate the order of operations, even though our operations here aren't necessarily the operations that we normally use. If you see square brackets in this context as well, they're just a different type of, damn. I am a little bit worried because I am pretty sure I just froze on my own computer, even though I can still see me on the surface. Okay, so the question is, can everyone still hear me?
Yes, we can.
Okay, I'm pretty sure this has happened to us before, and I'm going to very quickly be unhearable. But I'm going to try and do as much of this as I can. And we'll, yeah.
I'll Slack you. Just keep an eye on your Slack. I'll Slack you if you become unhearable.
Okay. Yeah, I probably actually won't even be able to see it. Okay, so I'm actually, all right, you're not going to be able to hear me for a second here because I'm just going to restart this computer. And so that,
For the people that don't know, the word surface is still Tyler, so he's a double agent right now. So I don't know if you ever mentioned this, but the way Tyler does it is he logs on through his main computer through Zoom, and then he has a second device, which is a Surface, where he actually writes his solutions, and he joins the Surface from he joins the Zoom through his Surface as well. So you see the solution through his Surface like kind of like a different person, and then he has his computer. So sometimes his computer gets stuck, but the Surface doesn't. So you can still write on the screen, and you can still see him like actively writing, but you won't be able to hear him anymore or see him. So that's what happens from time to time. And he had to restart his computer there, and I think he's back.
okay. Audio settings. All right, everyone should be able to hear me, I think, too.
Yes, we can hear you.
Okay, sweet. I am back. Now, unfortunately, I've lost the question, so I don't have the question either, because I have to, thank goodness for like solid state drives nowadays and just how quickly they restart. I absolutely love it. Gone are the days of the old crappy hard drives. Okay, sweet. So overwhelmingly, I think we said A. Did I get a chance to share the results?
You did for a sec. You did for a second, and then got. I don't think it does see that.
Right. Okay. So basically, right. So if you can see them, right, A was first and then C. So overwhelmingly, the class said A. Overwhelmingly, the answer is not A. So let's figure out why. So the question was, we wanted to figure out which of these sets was just the set 635, right? So this thing has two elements in it, right? The number 6 and the number 35, and that's it. This isn't an interval or anything like that. It's just a box that has exactly two things in it, the number 6 and the number 35. Now, the class answered this set, 2, 5 times 3, 7, okay? But this times does not mean that you take 2 times 3 and 5 times 7. That's not what this means. This is the collection of all possible pairs. Maybe let me write this in a slightly different way. Of all possible pairs where the first number is either 2 or 5, and the second number is either 3 or 7. Okay, does that make sense? Does everyone see that this is not the set 635, right? The set actually has 4 elements in it, not 2. And the things inside of this set are tuples, right? They're pairs. They're not individual numbers. Okay, so you want to be a little bit careful about that. Now, does everyone understand what the Cartesian product is, right? Like you just need to choose, you're going to write down 2 numbers. And the first number has to be one of these things, and the second number has to be one of those things. Okay, so that's how the Cartesian product works. Okay, so this is not it. So for B, we had 135 intersect 640. Okay, can anyone tell me what this set is? Order does not matter. Yeah, in a set, order does not matter ever. Yeah, so that's a good question, but exactly, yeah, it doesn't matter. So can anyone tell me, what is this set? So remember, intersection means take the collection of things that are common to both sets, right? Exactly, Rafid, exactly. And Edward, yep, that's a great way of doing it. Some people do write it like that. In math, though, we tend to use this special notation, and this means the empty set, right? It's the set of nothing. But Edward, that's a great way of doing it as well, right? So Edward kind of wrote it as like just the set with nothing in it, and that's absolutely correct. Okay, so this is the empty set, right? There's nothing in common to both of those sets. C, so we're going to do, and Brandon, hopefully you heard my explanation here. So the brackets here are going to do order of operations, right? So we're going to do the stuff inside of the brackets first. Good. So we're going to do the stuff inside of the brackets first, and then we're going to do set difference. So let's do this one step at a time. What is the union of the thing in the brackets? Okay, so what is the thing in the brackets? When I union these two sets, what do I get? Right, exactly, Jeremiah. Perfect. So 6, 35, 36, right? Union says put them together. Now, notice that 6 does not appear twice, right? Because a set can only have, like a set can't have multiple of the same thing in it. So when I take 6 and I union it with another set that has 6, the 6 only appears once, right? Exactly, repetition is not allowed. Now when I take 6, 35, 36, and I say, get rid of the 8 and the 36, what am I left over with? 635, exactly. And so this is the right answer. Now, a lot of students will often ask, well, exactly, Curtis. So this kind of hits the point. Now, a lot of students are often, let's kind of hit this. Let's make sure we understand this. They say, well, we said get rid of the 8, but there's no 8 here. So what do we do with it? And Curdy has exactly the right idea. We just disregard it. And the example I like to give is there anyone in this class who has blue hair? Does anyone have blue hair right now? Just as an example, if I give an example, I want to make sure there's nobody here who has blue hair. Okay, so, okay, yeah, it's too bad, but I'm going to assume nobody here has blue hair. So if I said everybody in the Zoom meeting with blue hair, get the hell out, what does that mean, right? So I'm going to take the set of things that I'm working on are all the students in this Zoom meeting. And I'm going to say, we do not allow blue-haired people in Math 133. All the blue-haired people get out. Well, okay, I told the blue-haired people to leave, but there are no blue-haired people, right? So nothing happens. We just kind of ignore it. And so that's the exact same thing that's happening here. I'm going to say 6, 35, 36. Here are the people I want to get out. I want 8 to leave and I want 36 to leave. So 36 leaves because it is in the set, but there is no 8. So it doesn't matter that you told 8 to leave. It's not there, right? So nothing happens. Does that make sense? Is everyone okay with that? Right? Yeah, this one's that example is definitely more fun in person because I definitely will try and I can just look around the class and see that nobody has blue hair. Sometimes somebody does though, right? Sometimes definitely some people have blue hair, right? Does it always work like that for whatever's in the 8? Absolutely. Okay, so what I also could have said is I could have said 8 and 36 and maybe heart. Okay, oh, that's a terrible heart. Okay, I could have told heart to get out as well. But of course there's no heart in the set, right? It doesn't even need to be numbers. I could have told anything to leave. I could have told all the guys in the set 6, 35, 36 to leave, right? And it wouldn't have changed the answer because there were no people in that set. So totally it works the exact same way and it doesn't matter what it is. If you try and remove something from a set and it's not in there, you just ignore it. Okay, and Rafid, so we got 635, intercept 636. And I guess exactly, you kind of jumped the gun on me, but that is absolutely right. The answer is just 6. Because when we take the intersection first, we say what number is common to both sets. Oh, there's only 6 in both sets. And then I tell the 35 to leave, but there is no 35. So the only thing I get out is a 6. Okay, so does everyone understand these operations? How did I get 836? It was in the question. Let me see if I can. Let me go to the question again. Right, so the 836 here was in the question. We didn't do any sort of computation there. I just had a direct message, which is where do we get it? And yeah, there was no problem because the question goes away, so you don't see it anymore. So you might not remember where it gets it. But yeah, the 836 was given to us, so it's gone. U is union, right? Is very conveniently the same thing. And Curdy, don't worry, I'll come back to D in a second. So U is union, so it says join the two sets, right? Just take everything and put them into one big old set, but you're not allowed, as Curdy pointed out earlier, you're not allowed repetition, right? So you're not allowed to repeat the sixes. And then wouldn't you be left with 6 and 36? Okay, well, let's do this. So, right, notice that these are different, right? One's 35 and one's 36. Right? And these are different. So when I want to say which numbers are common to both of these sets, the only number that's common to both is 6. So I would get 6 remove 35. Does that make sense? Yeah. Davis, so union says join them, like combine. Right? This is called intersection, and this says find the common, the stuff that are the same. We often think about these in terms of Venn diagrams, right? So if this is A and this is B, this is their union, right? So this is the union. And then the intersection is where they overlap, right? Right? Does that make sense? Okay, perfect. All right, right on. So let's do, actually, you know what? While we've got a Venn diagram up, why don't we do a Venn diagram question? So here we go. Let's do this one. Guys, you know what? It's just so appropriate. We might as well do it because we're here. Oh yeah, all my polls have closed and everything too. Stupid Zoom. Relaunch. There we go. Oops. Yes, though the slash goes the other direction, but yes. And actually that is important. The direction of the slash actually does make a difference, believe it or not. But yes, it is like the minus operation for sets, exactly. So yes, let me check. There's no name now. But Connie, yes, for your first thing. And let me think about the second one. It depends on what you mean by inverse, right? So what I think you mean is complement, and then it depends on what complement means here as well. Oh, I see what you're saying. Yes. Yeah. Yeah, you could write it like that. Absolutely. Jeremiah, yes. Yeah, it's those 4 pairs in the brackets. Exactly. Okay, 30 seconds because we're already at 2/3 of the class, which is pretty awesome. So let's do another 30 seconds, see where we go. Curdy, sure. Yeah, absolutely. Okay, let's see where we got. So we're going to end the poll. We're going to share the results. All right. So we seem kind of split on B and D. Now let me see. Is there any way D is going to be right? A minus A intersect B. Okay. Interesting. D is close. I think a lot of people, if you said D, you might have just, you were really close, but you actually want the intersection to be the union. If the intersection is the union, this is absolutely correct. But remember, that's an intersection, right? So we have to be a bit careful about that. Okay, in this case, let me actually just copy the question into my Surface because I don't want to like redraw out all these pictures and stuff. Okay, stupid Zoom is in the way, but whatever. I can just fix that once I'm in here. Okay, so the stuff that we're missing here is A intersect B, right? Okay, so here's the question. We want to figure out what this is. So I think what we should do is we should try and draw each of these problems, right? So for part A, so let's draw our Venn diagram. So we have A without B. Okay, so A without B is this part. Right? This is A without B. Does everyone agree? And B without A is this part. Right? Okay. And now it says intersect them. And if we intersect them, we're looking at where they overlap. So their intersection is empty. Again, if this was a union, it's not the middle part. It's where the blue and the yellow overlap. And you'll notice that the blue and the yellow never touch each other, right? So I've got my yellow stuff, that's A minus B. I've got the blue stuff, that's B minus A. And then I say, where do they overlap? And the answer is they overlap nowhere, right? Yeah, so this answer is actually empty. Now, if this were a union, this would be the correct answer, right? Do we agree? If this were a union, then absolutely we would get the shaded area above. But in this case, unfortunately, it doesn't work out because it's an intersection, not a union. Okay, so for B, well, I literally just said that, right? So B is the correct answer because we would combine them. And if we combine them, right, we notice that that is a union sign instead of an intersection. So that is the correct answer. There's value, I think, to doing the other ones as well, though. Let's just do them while we're at it. So C is to do A intersect B and then get rid of A union B. Okay, so let's draw that. Okay, so A union B is everything in both circles, right? Oh, sorry, it's intersections. Thank goodness, it's so easy to erase. A intersect B, right? So if it has something inside the middle part, it could also be A. If it has something inside the middle part, it could be A. No, direct messenger, I'm not certain what you mean, but by necessity, A minus B excludes the stuff in the middle part, right? All the stuff in the middle part got taken out. So there's just no way that the middle part is going to fill in. Like when I intersect the two sets from part A, it's totally empty. Yeah. Okay, so this yellow thing is A intersect B. And then I'm going to get rid of the union. Okay, so the union is everything, is all the blue stuff. So if I take all the yellow stuff and get rid of the blue stuff, what am I left with? Exactly, I'm left with nothing. Okay, and then finally for D, A minus A intersect B and B minus A intersect B, that's actually the same as A. Yeah, Caitlin, I missed yours too, but yeah, absolutely, you're right. Yeah, nothing. Okay, so it turns out here that answer D is actually the same as answer A, right? These two actually give you the exact same sets. Namely, they give you nothing. But you'll notice that in all three of these cases, we actually gave you the correct answer B, and then the other three answers was nothing, right? The other three answers were you got the empty set out, right? So are there any questions about this? Right? Like this is actually this stuff here. I know the yellow is a little bit hard to see, but that's that. And the blue stuff here is exactly that. Okay, any questions? When you write something with the, say, why do you put the part lower than to the left side? Not everybody does. That's true. So actually, you'll notice that in this question, we did not write them lower, right? But in the book, I probably do. And so you might be asking, like, why in the book do I do that? That's a good question. It's just to make notation clear, but it's not necessary, right? If you don't want to write it as like in a subscript, you don't have to at all, right? But to me, it just helps me kind of track which things are being subtracted. So that's why I do it. I'm not alone in that. There are definitely some other people do as well. Okay. If it was union in D, would this be correct? Agam, yes, absolutely, it would be. Why is C empty? Okay, so Davin, the yellow stuff is A union, or sorry, is A intersect B, right? That's the yellow stuff. And then we're going to get rid of the blue stuff. And you'll notice that the blue stuff includes all the yellow stuff, right? So if I take the yellow stuff and throw away all of it that touches blue stuff, I would get nothing left over. Does that make sense? And Louise, yes, that would also work. Okay, cool. Yeah. And so yeah, Louise, yeah, your answer is absolutely correct as well. Yeah. Okay. All right, let's do now something that we are going to really kind of lean on here is something called set builder notation. And so hopefully you watch the video on that because that's pretty important. So let's see how we do on this one. And remember, sets don't have to be numbers, right? So in this case, M is the set of all months in a year, right? And I assume that you all know the months of the year using our standard, calendar, whichever calendar it is, Gregorian calendar. Okay, so if you're using like the Aztec calendar or there are other ones, I don't know. I think there's like a Hebrew calendar. There is a, so we're just going to use, our Gregorian calendar. That's the one that we're going to use. No, yeah, unfortunately you can't change your answer. But again, it doesn't really matter if you hit the wrong thing because it's not worth marks, right? You know what your correct answer was. So even if you might have hit the wrong answer in doing the polls, just be like, okay, I hit whatever, but I meant to hit this, and then just see if your answer is correct. And I need to remind myself which months have 31 days because I definitely don't remember off the top of my head.
You have to use the knuckle trick, right? That's the one I use at least.
Yeah, that's what some people do. I'm not doing that. March.
It's 7.
July. Yeah, so there's, yeah. 1, 2, 3. Okay, I think I got it all. Yeah, it drives me insane, right? Like who decided that we should do 30, 31, and 28, and sometimes 29? Listen, you can't avoid leap years, right? Leap years are going to happen no matter what you do. And the reason for this is just the Earth does not go around the sun in 365 days, right? There's nothing we can do about that. But, well, maybe. No, I think actually it was the Romans, right? Because very famously, the original Roman calendar only had 10 months in it. And this is where July and August come from, right? Is Julius and Augustus Caesar. But famously, I can't remember what they were called, but the leader of the Roman Church would always add days to the end of the year in order to make sure that the calendar's balanced out. And I'm pretty sure our calendar is based off of that one. And then the Catholics, of course, Rome eventually became Catholic and so would have used that same calendar. So I think that's where that would be, but I'm not 100% certain. And I'm not a historian. And I also don't want to involve religion in this class because this is a surefire way to get out of control. Right? Exactly. And Devin, that's exactly what happened, right? Octo is the 8th month. November should be the 9th month, and December should be the 10th month. But July and August got inserted, and that therefore pushed them all up by 2, right? And that was the issue. But what it should be, so a week should be 10 days, right? Every month should then have exactly 3 weeks. So every month has exactly 30 days in it. So this gives you 360 days for the year. And then there should just be 5 days that are not part of any month, right? So you spread them out throughout the year. And it's, like the, I don't know what you would call it, the spring day, right? And it occurs like between March and April or something. And then there's like summer day, which occurs between like July and August. And so you take these 5 days and you spread them out, and they don't belong to any month. And then you have 365 days a month. And then when you need to add in a leap year, you just make a 6th day, right? Exactly, 5 days of holidays. And 100% they would be holidays, right? They should be holidays. So if we did this, everything would become so much better. And I think in 30 seconds, by the way, okay, I'm going to close it in 30 seconds. I think you all might be like, oh yeah, it's not a big deal, whatever, just deal with it. But if any of you have ever had to use a computer with dates or like program stuff with dates, it's an absolute nightmare, right? Like it's some of the worst stuff in the world, because think about it, every month is different. And every year is different. Okay, here, quick, true or false? Was the year 1900 a leap year? Yes or no? Okay, okay. So some of you are like really, half of you are yes and half of you are no.
Just divide by 4, isn't it?
1900 is not a multiple of 400. 2000 is though.
Wait, 1900 is a multiple of 4.
Not 400 though.
Oh, 400, sorry.
Okay, so here's the rule. A year is a leap year if it's divisible by 4, right? That's how we normally know it, right? So if the year is divisible by 4, it's a leap year, unless the year is divisible by 100, in which case it is not a leap year, unless that year is divisible by 400, in which case it is a leap year.
Excuse me?
Right. 1900 was not a leap year because it is divisible by 100.
Oh, but not 400.
But 2000 was a leap year because it was divisible by 400. Right? Rafid, the way you code that is just with a bunch of if-then statements, right? But it's very annoying. In fact, it's so bad that a lot of modern computers just pretend that 1900 is a leap year, and this actually is a major issue. Almost all Microsoft Excel files, for example, like all of Excel software thinks that 1900 was a leap year. So if you're using it to record dates that occurred before 1900, it actually records them incorrectly. And so it's a nightmare. Why? Okay, let me do this question and then I'll explain why. But basically, it's not 365.25. It's 365.248 something, right?
Interesting. I didn't even know that.
Brandon, yeah, and Brandon, actually, yes. It's not that they were competing, it's that they wanted it to be backwards compatible with IBM's software, and IBM software also made that same mistake. Yeah, so, but Brandon, exactly. Sorry, Aziz, what were you gonna say?
No, I just never thought of it like that before. It's very, very interesting.
Okay, and so yeah, Curdy, I can go into more detail in a second, but let's kind of nail this one first. So M is the months of the year, right? Well, let's just say months of the year. Right, okay, so E is the set of months such that M has 31 days. Okay, let's write it out. So I did it ahead of time. Double check me though. I'm pretty sure this is January, March, May, July, August, October, and December. Is that correct? Okay, that's a great question. Yeah, what is the point of little m and big M? Let me write out F first here, and then I'll tell you. M is after May. Is my E right? Does somebody double check that for me? So this is going to be June, July, August, September, October, November, and December. Okay, and so I got this question of, okay, perfect. So I got this question of like, what's the big M and the little m? So big M is the name of the set, right? It's the collection of all months. I don't want to write them all out, right? But it's January, February, March, etc. Okay, so it's actually a name. Little m is just a dummy variable, right? So little m is, it's almost like you remember in sigma notation when we'd say the sum from I equals 1 to n, and then we'd do something with the I, and it was just so that we could reference the I within the loop. Little m here is playing the exact same role. It's just a dummy variable so that I can refer to it later. So this says m has to be a month, right? So this says m is a month because big M is the collection of all months in the year. And then it has to also satisfy this property. So M is a month and M is after May. Right? So it just allows me to give a name to what I'm trying to reference, right? It just gives me a dummy variable that I can use to describe the things in this set. Does that make sense? Yeah. Isn't M a month that has 31 days? In E, right? This is a great question. So in E, little m is a month that has 31 days. But once I've finished the definition of E, little m becomes free again and I can reuse it, right? Like it's the definition of M is only local to the set E. But we could have called it something else. Like if this bothers you, we could definitely just call this something else as long as I replace it everywhere, right? So I could say X is a month such that X is after May or something like that, right? So again, even if you let me tangent here for a second, let's let S be the students in our class, like right here, right now, right? Students in our Zoom meeting, right? I could do something like, let's say T is the set of the students in this class, right? Such that S, what do I want? Has blonde hair, right? So this allows me to reference S, right? I'm saying little s is a student in this class and S has blonde hair. So what I would do is we could check whether each of you belong in this set, right? So I could go up to Edward and I could be like, Edward, do you have blonde hair? Edward, do you have blonde hair? Okay, no, so you are not in T, right? And then I could go up to Victoria. Victoria, do you have blonde hair? And I will answer your question in a second. Okay, Victoria, so you're not in the set. Is there anyone here who does have blonde hair? Just so I do have somebody who's actually in the set. Okay, yeah, Curdy, Aiden. Okay, so you two have blonde hair, and so you are in the set, right? And so with the little s here, so we have to clarify what the dummy variable means in an assignment. So Victoria, in this context, it's clear what the dummy variable is doing. just like when I write sum from I equals 1 to 10 of I squared, I here is understood to be a dummy variable that belongs to the sum. Does that make sense? Right, so you don't have to say anything beyond that. It's clear that it's a dummy variable in the context of what the set is. Okay, so yeah, so you don't have to explain what it is. It's fine. You do have to say where it belongs though, right? You have to say, oh, this is in the collection of all students in this class, right? And then you can check who's in this. Well, you know, it's just a nice example. And then you can check, like the idea is that this set is too big, right? There's like 76 people in the class right now. I can't write down everybody in the class who belongs to the set T. But what I can do is individually, I can check for each and every single one of you whether you're in this set, right? I would just say, do you have blonde hair? If the answer is yes, you're in T. And then I could check, do you have blonde hair? If the answer is no, then you're not in T, right? Does that make sense? So the S here is you. You are the S for the second, while the little s, while I check if you have blonde hair. If you do have blonde hair, I put you in the set. If you don't have blonde hair, I kick you out of the set, and then I go to the next student. And that next student is now little s. And then I check if they have blonde hair. If I do, I put them in the set. If they don't have blonde hair, I kick them out. And then little s is the next student. Does that make sense? Do you see how little s works there? Like I just let it, little s, run over all the elements in big S, and then I use that to check whether or not they belong to my set T. Is that okay? Mm-hmm. Okay, cool. So now we have these four statements, right? So the first statement A was that E union F is everything. Is this statement true? Okay, so I get some no's. So if the statement is not true, you should be able to give me a counterexample. Namely, give me a set which is not, or give me a month which is not in E union F. Oh, January is in there though, right? January has 31 days. Okay, so February is not in there, right? Exactly. So February is not in E union F. So Rafi, do you say you can't see my screen? Okay, great. So it worked out. Sure, and there's, yeah, exactly. There's other examples. April is another one. Is that it? Are those the only two sets or the only 2 months that are not in here? All right, so January, February, March, April, and then yeah, I think that's it, right? So it's just those two, but it's not everything. Okay, B is that E intersect F is equal to June, August, October, and December. Is that true? Okay, so we say, okay, so let me say this is not correct, right? Okay, and why is it not equal to June, August, October, and December? Okay, sure, yeah, June is not in both sets, right? That's what you're trying to say? So June should not be in here, right? June is actually not in E intersect F, right? It's after May, but it doesn't have 31 days, right? Okay, yeah, Caitlin, that's another way of doing it. July, right? Yeah, sure, July should be in there, or July should be in this thing. Yeah, that's another great way of saying it. Yeah, so there were two ways that this could have been wrong, right? And either of those is fine. Yeah, that's absolutely correct. Has anyone noticed by now that the union is the same thing as saying the word or? And that the intersection is the same thing as saying the word and? Does everyone know what I mean by that? Is everyone okay? Okay. So yeah, those are nice things to keep in mind, right? Is that the intersection is the same thing as saying and the union is the same thing as saying or. Okay, so B is not correct either. C is that September is in the intersection. Is that true? No, because September does what? If you had to explain it, right? September does not have, right? September has 30 days, or I would say September does not have 31, right? since September is not in E. Great. Okay. So it's not C. So process of elimination has to be D, but we can double check. So we say October, December. Now, is everyone okay with this symbol? Right? What does that symbol mean? Right? It means subset, right? And when we check subset, all we do is we say, is everything on the left inside of the thing on the right? It doesn't need to be equal. It just needs to be in there, right? And we know what the intersection should be. What should it be? It should be August, October, December, and July, I think is what I know I didn't write them in order, but I think that's what we decided they were going to be, right? July is in both, August is in both, October and December is in both. And yeah, these are both in here. So it is a subset. It stands for subset. In the same, it's very similar to like a less than or equal to sign, but it's, yeah, you can think of it as contains. I think that would be the better way to think of it, Jeremiah. If you want kind of a mnemonic, think of it as contained, right? So October and December are contained in E intersect F. I think that would be a little bit easier to remember. If it was October, December, and January, then it wouldn't be a subset. That's correct. Yeah, exactly, Curdy. So if January was over here, then we would write this, right? It's not a subset. Yeah. So October and December is a subset of August, July, October, and December. Exactly, Christian. Yeah, exactly. Okay. Does that make sense? Hopefully we're getting a little bit better at playing around with these set stuff. Okay, cool. Aziz, I imagine you have to leave to go do tutorial. Everyone just give me like, yeah, sorry, what?
No, I was like, that's the game plan. I was going to have that to start my tutorial.
Yeah, for sure. Absolutely. Everyone else give me like 2 or 3 minutes here, just refill the water and stuff. And then we'll come back and we'll do office hours because I'm sure lots of you have lots of questions about the linear algebra stuff. I know I have an eigenvalue, eigenvector question on the table and an octave question on the table. So we'll do that when we come back, but just give me 2 or 3 minutes here and I'll answer all your questions. Okay, everyone? And Aziz, see you later. Unless he's already gone. Maybe. Okay, I'll be back. Okay, let me take a look at these questions. You know what the worst thing about Zoom is? It makes you download all these questions. Okay, so Curdy, give me a second because somebody did actually message me before you about Octave. Gurpatab, I think that was you, unless I'm misremembering. Can you remind me what it is exactly you want me to do? Something about Octave, I think. Maybe you're not there anymore. Okay, so I think this was related to the question of like augmented matrices, right? And using Octave to actually row reduce, right? So yeah, okay, sure. Does anyone have a problem? Like, otherwise I can just make stuff up, but it would probably help if we actually had a problem that we could work on. But yeah, here, let's say that I have, let me maybe find my book and we'll see if we can come up with an example. So, sure, yeah, Davin, sure we can. Okay, let me pull up an example. Okay, so everyone, I'm gonna refer to my book. Okay, let's look at 3.21. Okay, so I'm gonna give everyone a second, grab the PDF of the textbook, and this is on page 83. Okay, so example 321, and it gives us a linear system, and it wants us to solve that linear system. Okay, so I'm gonna give everyone just a second to pull it up. All right, so this is the question, and solve this system and write it as a linear combination of the solution to the homogeneous system and the particular solution. Okay, so that's what you should be seeing. Oh yeah, here, let me maybe send it to everyone. So example 321, page 83, I think, according to my copy of the notes. Here, actually, just let me share. Let me just maybe share it. I should be able to share both of them. Share. Yeah, here. Why not just do this? Not page 83. Oh, okay. Maybe I must have made a change to it since I posted it on thing. But I think you can all see this, right? Okay, right. So let's say we wanted to solve this equation and we didn't want to plug all these numbers in. And you can see this is augmented, right? So I know that a lot of people have been worried about the fact that this is an augmented matrix. So what I'm going to do is I'm going to define a matrix. I'm going to call it A, and I'm going to put this matrix in, and I'm going to include the augmented column as well. So even though I can't draw that vertical line, it doesn't matter. I'm going to put it in anyway. Okay? So I am pretending that that vertical line is right here, right? And hopefully, remember, always, anytime you're putting in Octave, double check your numbers, make sure you put them in correctly, because if you didn't put them in correctly, you're going to get the wrong answer. And this is a really bad place to lose marks. So I think I double checked and I think I put them in correctly. So we're going to remember that there's a vertical line right here. Okay. And then what I'm going to do is I'm just going to say, hey, Octave, you want to row reduce that for me? And this is what you'll get. And again, we're pretending that that vertical line is still right here. And if we compare this matrix to this matrix over here, which is the row reduced version of it, actually in RREF, notice that these are the same, right? These matrices are exactly the same. So yeah, what you're going to do is when you have an augmented matrix there, you are just going to pretend that the line is still there. Okay, you're just going to pretend that the line is there when you put the matrix in, and then row reduce like normal and still pretend that the line is there when you're done. And that will give you the reduced the reduced row echelon form. Now from here, you have to do this part by hand still. Okay, you like Octave, I don't think can do this for you, to my knowledge. So you still have to do this part, but the hard part is actually doing the row reduction, right? Yes. of any size. Like it doesn't need to be square, and legitimately Octave can, I have put million by 1 million matrices into Octave, and it does it very quickly still, right? So yeah, you definitely don't need to worry about size in any way, shape, or form. No. Usually you have some sort of data that you can read from, right? So you'll have like real life data in like an Excel spreadsheet or something, and you can import it into Octave. That's a little bit tricky, but you can import it into Octave, say to make it a matrix and then row reduce it that way. And Octave goes like that. Octave is very quick, even by million, right? It's not that bad. Okay. Does that make sense? Does that, Gurpratap, does that like take care of your question, right? Like you basically just treat it as if that line was there. Okay, so well, Agam, let me see what that question is, because somebody asked, I've been asked to do a couple eigenvalue, eigenvector things. So maybe let's just take a look at what this question is. Sure, okay, let's do that in a second, because we can't do that in Octave. So someone very quickly, I think, wanted me to do, let me do an eigenvalue, eigenvector thing in Octave, then I'll do Curdy's stuff, and then I'll do 322, okay? So that's going to be my current thing. So let's find an eigenvector eigenvalue problem. Am I going in the right direction? No, I'm not. Okay, so here's example 3.47. Here's this big old 3x3 matrix, and you can row reduce it if you want. I'm not going to. So I'm going to plug it into Octave. 1, -1, 0, -1, 2, -1, 0, -1, 1. Hopefully I've done all that correctly. Now, when you use the EIG is how you compute eigenvectors and eigenvalues using Octave. Okay, what is the order here? Right, that's what we want to use. So I'm going to create, this is the output I'm going to use, because what I want to do is when I compute the eigenvalues and eigenvectors, I'm going to get out both the eigenvalues and the eigenvectors. So I have to tell Octave what to put where. So maybe let me write this as vectors and values, right? So I've got vectors and values is equal to eiga. If I hit enter, this is what I get. Okay, now this looks gross. So we gotta, we have to parse this a little bit. So 9.96 times 10 to the -17, that's 0, right? This number is 0. It's not exactly 0, but it's basically so small that it might as well be 0, right? So you kind of have to take a little bit of interpretation with Octave there. And this is definitely 1, and this is definitely 3. So if we've plugged our matrix into Octave correctly, the eigenvalue should be 0, 1, and 3. And I come over here and I check this, and what did we get? 0, 1, and 3. Those are our eigenvalues. Perfect, right? Now, the eigenvectors are a little bit nastier. Remember, each of these eigenvectors are designed so that their norm is 1. Now, we don't talk about norm in this class, but asking your eigenvectors to have norm 1 is usually something you want to do. But you're going to have to eyeball this. So if I look at this first column, this is the eigenvector for this eigenvalue, okay? And what I notice is that all the numbers here are the same. So therefore, I'm going to get 1, 1, 1, or if you want -1, -1, -1. 1, 1, 1 is an eigenvalue of 0, okay? And if I come over here, did I find the eigenvalues of 0? Oh, hey, look at that, I did. So I said when lambda equals 0, we row reduce, and we get 1, 1, 1, right? And that's the same thing as this, because any scalar multiple works. So what I'm looking for here is a relationship between the variables, right? Between the numbers. Here I notice that they're all the same. So I'm going to let one of them be 1, and that makes the rest of them 1. Does that make sense? For number 2, so column number 2 here corresponds to this eigenvalue. Again, this number is basically 0. If you see something like 10 to the -17, that number is 0. And then the first thing and the last thing are the same, but different signs. So I'm going to say -1, 0, 1 is an eigenvector for 1. And if we check lambda equals 1, we get 1, 0, -1. Okay, I said -1, 0, 1, but those are the same because you're allowed to use any scalar multiple. Right? Does that make sense? Right, like that. And then column 3, so this is going to be the eigenvector for this thing, for this eigenvalue. And it looks to me like row 2 is twice row 1, right? Like, yeah, it looks like if I were to double the 4.08, I would get -8.16. So I'm going to guess 1, -2, 1 here. And if I look over at the answer, yeah, the answer is 1, -2, 1, right? And legitimately, yeah, it does save a lot of time. And in fact, there's a little thing that you can do. You're going to have to, I don't necessarily recommend doing this, but one of the things you can do is, let's say you get this thing right here. So I've saved all the eigenvectors into something called vectors, right? So I can access it. Now, if I recall correctly, does this work? Right. So if I use this notation, I want vectors, all of the rows of column 3. So that's just going to pull out this column right here. Right? You notice that's true. So this notation just pulled out the 3rd column. So I said all rows, that's what the column means, all rows and column 3. And then what I would do is I'd say, okay, the smallest thing in here is 40825. So I'm going to divide everything in vectors by 0.40825. And that gives me the eigenvector now where it doesn't look nasty, right? 1, -2, 1. So I don't think that's necessary, and I wouldn't waste time learning that like that notation. But that's something you can do. Would you ever have to do anything that required us to use Octave because it's just so much row operations that it can't be done by hand? Yes. See you, Davin. So I got a direct message asking, would you ever ask us to do anything that basically required Octave? Let me say the following very loud and very clearly. When we wrote the test, we assumed that you had access to Octave, right? Which means that we have given you a system which is big enough that you do not want to do it by hand. You could do it by hand, but you really shouldn't, okay? So 100% we will expect you to use Octave. Octave is not that hard to use, and we've given you the, an online thing where you can use Octave, so you don't have to install it if you don't want to, and you're 100% allowed to use it. We expect you to be able to use Octave, and so we've given you a system that is fairly big in the term test. Okay, let me be very transparent about that. You could do it by hand. You shouldn't. Okay, you have 24 hours. So if you really feel like doing it, you can, but you shouldn't. How did I convert that matrix to negative blah, blah, blah? It was just, yeah, so the command I used was just this one right here. Okay, and it said output, so the vectors has to come first. So it said store the eigenvectors in this variable. You could have called it whatever you wanted, and store the eigenvalues in this variable called values. So you can watch here, if I type values, it repeats this matrix, right? And vectors are the eigenvectors. So that's just how I store them. Now, if you just call eiga, then what it's just going to do is just give you the eigenvalues, okay? You won't get the eigenvectors out. So you really, if you do want the eigenvectors, you have to use this notation right here. Okay, so if you just use eiga, you don't get the eigenvectors. You have to include this notation if you want them. Okay, everyone's good? That makes sense for Octave? Uh, 1.5 from assignment 4. Okay, sure. Let me get to that. I have a couple questions lined up before that. Doug, yes, I believe it is all in the cheat sheet. Okay, so Curdy had a question, and then we had 322 from Agam. So let me just look at Curdy's thing. Now, Curdy, you sent that to everyone, right? So they can all see it, hopefully. That wasn't just sent to me. Yeah, I think you sent it to everyone. That's good. Okay. So I'm looking at the files that Curdy sent everyone. And actually, I might as well just share my screen again, right? So that everyone can see them. You don't have to like download it and stuff. Which one is it? Here it is. Okay. And I guess these are in the opposite order. There we go. So here's the question. Yeah, so they're in the chat higher, but I'm also sharing them on my screen if you want to see them. Yeah, no problem, no problem. So here they are then, and if you want them without having to download them, you probably want to screenshot it or so. Okay, so Curdy, what was bothering you? Express this as a linear combination of V1 and V2, and then yeah. So can you specifically say what was bugging you? I got up until REF, but I don't know how she proved after that A1 and A2 are linear combination. Okay, so you got up to REF, which is basically this. Note that the components of V1 are the coefficients of A1 and the components of V2 are the coefficients of A2, so the initial coefficient matrix looks like this. Wait, am I reading this in the wrong order? Oh, just how they got the answer here? Is that what you're saying? Like, how did they go from, right, okay, how did they go from this to this? Okay, so this isn't RREF, right? So I'm gonna share my surface again, okay, so that I can read it. Right, okay, so she's cheating a little bit. She jumped a step. Okay, so the matrix, let me just repeat the matrix that was there. So the matrix that was found was this. So 1, 1, maybe let me use square brackets because that's what we've been using. 0, -2, 0, -1, -1, 4, 2. So what the TA did, basically, is it 3, 1, 1, -1, 0, -2, 4, 0. Where's the 3? Yeah, that's part B, I think, right? Yeah, it's part 3. Okay, if this has a solution, then we're done, right? Then we've written -1 to -1 as a linear combo of 1, 2, 3, and 1, 0, 2. Now, are you fine with the fact that a solution to this gives you the linear combination, or should I talk about that as well? Wait, which vector? 1, 2, -1? It was in the question. Right? So the question is, write -1 to -1 as a linear combination of V1 and V2. Okay, right. Okay. So are you fine that a solution to this system will give you a linear combination? Okay. So we need to solve this system. Now, the system isn't in RREF. I would recommend finishing it. However, at this point, you could stop and solve this linear system as it is currently written. Okay, but if we continue to put this matrix into RREF, right, I would do 1/2 or -1/2 row 2 into row 2. So I'd get 1, 1, -1, 0, 1, 2, 0, -1, 2, right? Add row 2 to row 3. One, 1, -1, 0, 1, 2, 0, 0, 0. That's fine, still has a solution. And let's do the last step. So let's do negative row 2 plus row 1 into row 1. 0, 1, 2, 1, 0, -3. Did I do that right? Negative that plus that, so that'd be -2. Yeah, that should be -3, right? Oh, no, sorry, this should be -2. Right. And then if I add negative that, I will get, so if I do that, I get -2. Those still cancel. And then negative that plus that should give me 1 here. Did I row reduce that correctly? Yes. Does everyone agree? Okay, so our solution, right? This is the A1 column. This is the A2 column. So like if we were to write down this linear system, we get A1 equals 1, A2 is equal to -2. Yeah. Definitely put it into RREF. I think it helps. Like I think the TA kind of jumped the gun there, and it's the exact same thing in B. In B, they didn't finish it to RREF, but if you take that matrix that's in part B and you finish it and you put it into RREF, you'll see that you get a one of these rows, something, right? Which we know means that you have no solution. So exact same thing in part B, you have that as well. So if you finish it, put it into RREF, you'll see you get one of those, and that's not allowed. Right? They just kind of stopped a little bit early once they could see that there wasn't a solution. So I think basically, yeah, no problem. I think basically what the TA is doing at that point is like, I can look ahead. Like for me, if I get to this matrix, I can now solve the system in my head, right? Because basically what I do is I look at this and I say, okay, row 2 and row 3 are basically the same. Ignore row 3. Okay, A2 is equal to -2. And if I plug that into this equation, I get A1 minus 2 has to be -1. Oh, A1 is 1. Right? So the TA, I think, got to this point where they could kind of just solve it in their head and then jump to step. And that's probably what threw you off a little bit. And I don't necessarily expect all of you to be able to solve it in your head. But I think that's maybe where the miscommunication came in. Okay, so Agam had 322 from the PDF. And don't worry, I remember that there were other questions, but honestly, I kind of forget it. Oh, Theodore, right, 1.5 from assignment 4. Okay, so that's on my to-do list. Let me write it down so I actually don't forget. 1.5 from A4. Okay, so 322 from the PDF. Sure, yeah. If you want, throw it in, and then I'll see if I have time to look at it. So let me share with everyone what 322 is, just so you can see it. And I think this is it. Okay, so 322. Agam, this is the question that you wanted, right? I just want to make sure my numbering is the same as yours. Okay, so this is the question right here. Everyone, if you don't want to like pull up the book and take a look at it, you can like snap a screenshot or take a picture of it right now just so you have it. Okay, so I'm going to close it in 5 seconds or so here. Okay, and I'm going to reshare my Surface so I can write on it. What is going on, Surface? Okay, so we have the matrix. So we've got this matrix big C, and it's C01, 2C, C1, C squared, 0. Okay, so the first thing you could do, if I gave you this question at the beginning of the course, what you could do is, so a matrix is invertible if and only if it's when you put it into reduced row echelon form, you get the identity matrix, right? We know that has to be true. And it says in particular, also find what the inverse is. So remember, when you want to find the inverse, and this is not the way I necessarily, well, actually, we kind of have to do this no matter what. But how do you find the inverse? you put it into a big ol' augmented matrix and you row reduce. Right? So I'm going to row reduce this matrix and I'm going to try and turn it into the identity matrix. If I get the identity matrix, it is invertible. Now, in the process of doing this, I might have to do things like divide by C or something like that, which would tell me that my matrix is not invertible, right? So if we go through it, and I guess we can actually do it. So let me see. So I'm going to do, and everyone double check my row reduction, right? Because I'm doing this live. So -2, row 1, oops. So I'm going to do -2, row 1 plus row 2 into row 2, and then negative row 1 plus row 2 into row 2. So it's going to give me C0, 1, 1, 0, 0. Okay, -2 times the first row, so that cancels out. That gives me C. This gives me -1, -2, 1, 0. Negative first row, C squared, -1, -1, 0, 1. Okay, did I do that right? I think so. Okay. And then I'm going to do -C times row 2 plus row 3 into row 3. So C0, 1, 1, 0, 0, 0, C -1, -2, 1, 0, 0, 0. Okay, so -C gives me C -1. And then -C times row 2, so that's going to be 2C -1. And then -C, and then 1. Negative row 1 plus row 3. Is there a reason why you want to do? Oh, yeah, you're right. Thank you. Okay, makes sense. So already here, I am assuming that C is not 0. So when I do this step, C can't be equal to 0. Now we're going to get this in a different way in a second. Basically, when I divide row 2 by C in order to get a 1 there, I'm going to get this condition. But if you want to multiply, actually, I guess C could be 0 here, right? You could add you could add 0 times a row into something. It would just be dumb, but you could do it. There's nothing illegal about it. Okay, and gross. Okay, we're gonna just keep going. Do I want to try and normalize this at this point? I guess I could. So what I'm gonna do is I'm gonna do 1 over C -1 row 3 into row 3. So I'm gonna get 0, 0, 1, C 0, 1, 0, C -1. So this will be 2C -1 divided by C -1, -C divided by C -1, 1, -2, 1, 0, 1, 0, 0. Okay, and so C can't be equal to 1 here, right? Because you can't divide by 0. And we're going to keep going. So now I'm going to do row 3 plus row 2 into row 2. And so anyway, it's long, right? But hopefully you just see this is what you do, right? You just keep doing this. And I guess we're going to do negative row 3 plus row 1 into row 1. And then we're almost done once we've done this. So we're going to get 2C -1 over C -1, -C over C -1, 1. Okay, so if I add these, so this is going to give me on the side -2 plus 2C -1 over C -1. So that's going to be -2C plus 2 plus 2C -1 divided by C -1. These cancel, so I'm going to get 1 over C -1 here. If I do the same thing, so I'm just straight up adding them. So I'm going to get 1 minus C over C -1. So it's going to be C minus C. So this is going to be -1 over C -1. And then this is just going to give me 1. Okay, and then if I do that, oh, this is not a lot of fun. I'm not enjoying this. So I'm very, very sad that you made me do this. 2c minus. Oh, shoot. Right? Oh, no, yeah, that's fine. So negative, so I'll go 1 minus 2c minus 1 over c minus 1. So that's going to be c minus 2c. So that's going to be negative c minus 2. And then if I do that, so this is going to be c over c minus 1, and then negative 1. Right? And then I just need to divide row 1 and row 3. So that give me 1, 1, 1. Negative c minus 2 divided by c times c minus 1. 1 over c minus 1, negative 1 over c. 1 over c times c minus 1. Negative 1 over c times c minus 1. 1 over c. 2c minus 1 over c times c minus 1. Negative 1 over c minus 1, 1 over c. Okay, so c also can't be equal to 0. Right? So it's invertible for any of these two numbers. And if you give me any number c, that is the inverse, right? This is the inverse matrix right here. Okay, does that make sense? I mean, it's basically like you do, yeah, absolutely could be. Right? Because then like, what are you going to do? You're going to use Octave. But here's the thing. So I found the values of c for which this matrix is invertible by virtue of finding the inverse. Now let's say, here's probably what would be more likely to be a term test question. So let's say same matrix C, and I just said find the values of C for which this is invertible. Don't find the inverse, just find the values of C for which this is invertible. What would you do? Okay, don't find the inverse. Okay, yeah, Brandon, sure, I see it. Yeah, but can anyone give me an idea? What would we do? Right, exactly, the determinant, right? So the determinant tells you precisely when a matrix is invertible, right? So a matrix is invertible if and only if its determinant is not 0. So let's compute the determinant of, this matrix. And let's say I go over, obviously choose one of the things that has a 0 in it. So let's say I expand over the third column. So I would get 1 times negative 1, right? So I'm currently here. So this is row 1, column 3, times the determinant of 2c, c squared, plus 1 times negative 1 to the row 2 plus column 3 times the determinant of c0, c squared, and then plus a bunch of zeros. This is going to be, this number here is just 1. So this thing becomes 2c cubed minus c squared. This number is negative 1. So I'm going to get minus the determinant of this thing, which is just c cubed. So I get that the determinant is what? Just c cubed minus c squared, which is c squared times c minus 1. That's going to be 0 precisely when c is equal to 0 or 1, right? And that's exactly what we found down here, right? I said, I was answering sort of different questions, but when is it not invertible? When c is 0 and when c is 1. So you can see the determinant is a way easier time of doing this. If you just want to actually find the values and not the inverse, this ends up being way faster. So the matrix is invertible if the determinant is not 0. So c being equal to 0 and 1 give me non-invertibility. Any other number gives me invertibility, right? So these are the values for which c is not invertible. And those are the only values. So every other number, the matrix is invertible. Right, exactly. 0 and 1 are the numbers it can't be, right? Because you don't want the determinant to be 0. That's bad. Right, so if you figure out where the determinant is not 0, you just let C be anything else. Does that make sense? Right, if C is 0, you can't find the inverse. Also, if C is 1, you can't find the inverse. Right, yeah. But remember that when you're solving for 0, you're finding the values for which the inverse does not exist. Right, it's the same thing when you're doing eigenvalues and eigenvectors, right? When you're computing the zeros of the characteristic polynomial, the characteristic polynomial is the determinant. And you're specifically finding the zeros because you don't want that matrix to be invertible, right? That's the critical point. When you're finding eigenvalues, you're finding the values for which the matrix is not invertible. Okay. All right, so let's see. It depends on what you mean. Like if I just give you a matrix and there's no like variable, then no, right? Like, but it very much is going to depend on the matrix. So for example, if I give you this matrix, this is invertible for all C, right? Because what's the determinant of this matrix? Anyone remember? Exactly, it's 1. Why is it 1, Agam? Right, triangular matrix. Brandon, exactly, it's triangular. So the determinant is precisely the product of its diagonals, right? So it's just 1 times 1 times 1, so the answer is 1, right? So this matrix, you can see its determinant does not depend on C. So this matrix is invertible no matter what value of C you put in there. You can put in C equals 0, you can see C equals 1,000,000. It doesn't matter. This matrix will always be invertible, right? And in fact, what is the inverse of this matrix? Well, you all can more or less figure it out without having to compute it, because this is precisely T13C from the homework, right? So it says take, do this row operation, R1 plus CR3, and put that in R3. That's definitely an invertible relationship, right? You knew exactly what you did. So if I gave you that matrix after that row reduction has been done, you can definitely undo that step, right? You added C times row 3 to R1. How would you get rid of it? You would subtract C times R3 from, or sorry, into R1, right? So what should the inverse be? The inverse should be row 1 minus CR3 into row 1, right? Does that seem reasonable? So if I added C times row 3, the inverse should be to subtract 3R3 or CR3, right? So we would hypothesize that T13 negative C is actually the inverse of T13C. And you can check. You can see if it's true. I'm sure what's up.
So, Professor, I just found determinant by computing it. I didn't figure out the triangle method, but for the triangle method, all the elements except the diagonal ones should be 0. Here C is not equal to 0.
So you mean in terms of computing the determinant?
Yes.
So in the determinant, as long as all the numbers beneath the diagonal are 0, then the determinant is the product of these numbers, even if C is not 0.
Okay, so it should be beneath it.
Or above it. So if it's the other way, so if I did something like 2, 3, negative 7, 5, 6, 2, 0, 0, 0. So now here all the numbers above the diagonal are 0. Nonetheless, the determinant of this matrix is 2 times 3 times negative 7.
Okay, I thought that both should be 0, above and below.
I mean, it's certainly true. If the diagonal are the only non-zero elements, It is true that the determinant will be the product of the diagonal, but you don't actually need that the matrix is just a diagonal matrix, right? You only need that it's upper or lower triangular. And I'd suggest that you try it, right? Compute, let's like make these arbitrary numbers here. So like A, B, C, D, E, F. Here's a nice little example. Try actually computing the determinant of this matrix and convince yourself that the answer is A times C times F. We did an example of this or like this when we did, I don't remember exactly what it was. It was like last week's poll 5. I think it was question 5 from last week's poll questions, where I gave you this big 5x5 matrix and I said, let's compute the determinant. And we talked about, oh, hey, it turns out that it's just the product of the diagonal elements.
Yes, I remember that 7x7 matrix, something like that.
Yeah, so to even go back and look at that problem, and the video of that should be up as well. So if you want to take a look at that, it might clarify. But I mean, you can compute this yourself too, right? Like right now, you could just do this and see that you get the product of the diagonal, right? No matter what B, D, and E are.
Yes, it's ACF.
Sorry, what?
It's ACF only. Like it's
Okay.
getting the product
Okay,
of diagonal elements.
Yeah.
Thank you.
No problem. If that was on the test, would that be a valid reason? Explain a triangle method? Yes, I would say this matrix is upper or lower triangular, and therefore the determinant is the product of the diagonals. And you should say exactly that. Jeremiah, how can negative C be C inverse? I'm not saying that negative C is C inverse. I'm saying that this matrix should be the inverse of this matrix. Okay, and we can check it, right? Like, let's find out. Maybe I'm wrong. But so this should be 1, 0, negative C, 0, 1, 0, 0, 0, 1. And this is going to be 1, 0, C, 0, 1, 0, 0, 0, 1. And if I multiply these two matrices, what am I going to get? So I'm going to get 1, 0, 0, 0, 1, 0. Okay, my zeros are really sloppy here. And then C minus C, 0, 1. And yep, that is the identity matrix. Right? And again, the reason that I was able to guess this, right, without actually ever doing any computation, the reason I was able to guess this is because I know that T13C does this row operation, right? By definition, it does row 1 plus C times row 3. So its inverse should just be to undo that row operation. And this row operation undoes the previous one, right? If I add 2 times row 2 to something, if I want to undo that, I'm going to subtract 2 times row 2. And that's how I knew that it would work out. Okay, does that make sense? Okay. So A4 1.5, someone wanted me to kind of go over that. So in question 4, if you row reduced, then, and our goal here was for you to row reduce to the identity. So you can see in the solutions that we have a bunch of row operations that we did, right? So we did row 2 minus 2 row 1. In fact, we only use the T matrices, right? So we did this, and we did row 3 minus 3R1 into R3, and then we did R3 minus 4R2 into R3. So these were the row reduction steps that we had done in the previous question. And you didn't have to use these, right? You definitely could have done your own. Right? Yeah, and if you do them in a slightly different order, it's totally fine. As long as your techniques are valid and you eventually get to the identity, this is totally fine. And so this row operation here, this is T21 negative 2, right? And then this is T31 negative 3, T32 negative 4, T13 negative 5, and T234. right? So those are those matrices. And then you apply them to A like this, right? So the first one goes immediately to the left, and you apply them like that, right? And that's how you do number 5. Yeah, maybe it is. You are right. Yes. Wait, let me see exactly how I wrote down what Tij is. So Tij of C is Ri plus Crj into Rj. And so this row operation, oh man, it's written in a weird way. Oh, because this is row 2. I screwed this up. So this was row 2. So this is, yeah, so this is in fact T21 negative 2. I'm sorry, I just screwed up what it was. Yeah. Yeah. Right, because I wrote did it map to R1 instead of R2? That was my mistake. I screwed up. Yeah. Yeah, so Teodora, that helped, right? That made sense? Like I was just figuring out what the row operations, how they corresponded to the T's, and then put them down. Okay, awesome. And then Brandon had no problem. Brandon had a question about 4-7. Did anyone else have a linear algebra thing? Brandon, I'm not trying to throw your question to the back. It's just, I think people are a little bit more worried about linear algebra. And so I do just kind of want to knock those out of the park first, if that's okay. Yeah, Shanayu, why don't you go ahead? And then Curdy, we can do hand eigenvalue, eigenvector.
Hi, Professor. Actually, my question is not relating to like solving, but
Sure.
I did I think the linear algebra quiz or
Concept quiz.
something
Yeah.
for the bonus mark. How do I get to know the answers for that?
If you have particular questions that you want to know about, you can just ask them on Piazza and I'll post them.
I actually posted a private message on Piazza.
Okay.
I shared a screenshot of my page.
Mhm.
And like, is it possible if I could get answers to all the questions?
Sure.
Just so that I know what's wrong and what's right.
Yeah, we could probably do something like that. Just give me a second. Give me a little bit to try and compile them because I actually have to go through and do it. Do you still have the ability to see the questions and the answers, or can you not see anything when you like?
No, right now it just says that my quiz is muted. I can't even see how much I got right.
Okay, sure. I might be able to fix that actually. Let me see if I can do that right now. And then maybe you'll be able to see
it. Is it possible if you could maybe share me the answers on the Piazza post?
Yeah, I mean, I don't have them in my head, right? Like I don't even have them written down. I would actually have to solve them on the fly. But what I want to see is if I can at least make it so you can see what the answers are, right? Or what the questions were, so you can go back and see like what your answers were.
So how will I get to know the answers? Will you post it or?
Yes, actually, there's an option here to let you see what the correct answer is. So let me see if this works. Okay. Check again now and see if you can actually see the answers because I've made it now so that you can see it. I don't know if it waits until the end, like if it's going to wait until the quiz is done to show the answers, but check it now and see if you can see.
I think it still says it's muted.
Okay. Let students see the correct answer. Only one attempt. Let students see the quiz responses. Incorrect questions will be marked. Allow multiple attempts. Require an access code. Okay, yeah, I'm gonna have to go through the answers then and put them up. Actually, I might just be able to tell you here based off of show question details. Yeah, give me a second. I'll just make a PDF of this page and then I'll put it on Piazza. But I don't want to do it right now. Right. Okay. So Shani, that's fine. I don't know if you responded from there, but I will make a screenshot of that page and I'll just post it to Piazza for you. Okay, cool. You might have to remind me though, depending on how it goes tonight. Like if you don't have it by say noon tomorrow, maybe just send me another message on Piazza, be like, hey, we talked about this in class. Can you just send that to me? Okay. So, because you might need to remind me depending on how busy I get tonight. Okay, so it seems like a bunch of people want a question about eigenvectors and eigenvalues kind of by hand. I'm going to have to pull up a question from the notes for this because I'm not going to be able to make one up on the fly. I mean, that's not true. I totally could. Maybe I should try and make one up then, just so that you have a new question. So, let's see how this worked. Whew. Okay, big ugly number, but fine, whatever. Okay, so Agam, it depends on what you mean by word question, right? Do you mean just like find the eigenvalues and eigenvectors of a matrix, or do you mean like if there was more questions in there? -5, 30, -11. Right? Because for example, the turtle question, yeah, I don't have any good examples of those right now, but I might be able to post something for you if you give me a bit, or maybe post something on Piazza being like, hey, you know, Tyler mentioned in lecture that he had a question like this. Tyler, can you post it? Just so I have a written reminder somewhere. Because I don't have any off the top of my head. They're actually really hard to make. They're not the sort of thing I can just make up off the top of my head. But we do have one, right? Which is actually where the turtle question came from. Okay, so let's solve the eigenvalues and eigenvectors of this one by hand. I will post the turtle question only on Piazza. Yeah, post it on Piazza. I'm not sure if you're saying something else, but yeah, post it on Piazza just so that I have a written reminder to do it, and specifically say that I said I would do it so that other TAs don't, or instructors don't involve themselves. Okay, so I've made this question up on the fly. I'm really hoping it works out. If it doesn't work out, we're in trouble. But I'm probably going to go through it a little bit quickly. So, but scream if something doesn't make sense. Okay, so first thing we need to do is find the characteristic polynomial, right? So the characteristic polynomial, P lambda, is the determinant of A minus lambda I. So the determinant of A minus lambda I, if I compute what A minus lambda I is, that's 14 minus lambda, -5, 30, -11, minus lambda, right? You basically, lambda I is just subtract the lambda from the diagonal elements. And I know how to do this. This is AD minus BC, right? -11 minus lambda plus 150. I am really worried about these numbers. Lambda plus 11 plus 150. Okay. So if I add 14 and 11, I should get -3, right? If I times 14 and 11, what is that, 154? Oh, hey, look at that. That works out pretty nicely. So lambda squared -3, lambda -4. So that's equal to lambda -4, lambda plus 1. So that gives me, right? So I'm trying to find the roots. So lambda is equal to 4 and -1. Okay. Why do we think it's -150? Yeah, but you have to subtract it, right? It's AD minus BC. So in this case, right? Everyone's okay with that? So it's minus -150, right? right? We're good on that. Now, Kurt, you say the third row. So which row? So this third row or the one beneath it? Beneath it? Okay. So this is, I just expanded out that polynomial above, right? Is that okay? Like you might have to pull out a calculator to do it. I can multiply 2-digit numbers in my head, right? But like, so I did that. And then I did a negative 154 plus 150. So that just gives me -4. And then I factored this polynomial into lambda -4 and lambda +1. And since I'm trying to find the roots are precisely where this is equal to 0. So lambda = 4 as a root and lambda = -1 as a root. Does that make sense? You can always, if you can't factor out, then you either have no eigenvalues, which is possible, or you're going to have to use a computer. Like if you can't factor it nicely, you might have to use a computer to do it. Right. Now you can imagine in practice, I would give you something that factors nicely or just didn't factor at all. But in real life, 100%, you can have things that have nasty eigenvalues, right? In real life, life doesn't care about whether it gives you integers or not. Okay, so I will do, you guys choose. Do you want me to do the lambda = 4 or the lambda = -1 eigenvector? 4? Okay. So now what I'm going to do is I'm going to take lambda = 4 and I'm going to plug it back into a minus lambda I, right? So I'm going to look at a minus 4i. So what is that actually? Let me just, so that's going to be 10, -5, 30, -15. And I'm trying to find the homogeneous solutions to this system. Okay, and is everyone fine? Everyone sees where 10, -5, 30, -15 come in, right? You'll notice that is actually this matrix, but with lambda = 4 plugged into it. Right, exactly. Okay, so now I'm going to row reduce this matrix. Hopefully you all see that the third, is it meant to be equal to 0? Well, I'm trying to find the is what meant to be equal to 0, Jeremiah, I should probably say. Like, right, I have to find the homogeneous solution. So these ones have to be 0. Is that what the question was, or maybe I misunderstood? Yeah, it's okay. Okay, yeah, because I need to find the homogeneous solutions. So if I row reduce this, I can row reduce this in my head. Hopefully you all agree that this is it though. So I know the second row is just going to be 0 because I can see that if I do -3 times row 1 plus row 2, yeah, row 2 disappears, right? And then so I divide row 1 by 10 and I get this. So I skipped some steps here, but is everyone okay that this is our REF? Okay, great. So this does, right, here's my leading one. So I have x1 minus 1/2 x2 is equal to 0. I'm going to set x2 to be my parameter t. And so I get x1, x2. x1 is equal to 1/2 x2. So that's 1/2 t, like that. And then I can factor out my t, 1/2 1. Here is your eigenvector. You can use any multiple of that as well if you want. So you might want to use 1, 2 instead, right? Instead of 1/2 1, just so that you don't have fractions. So you can multiply it by 2 if you wanted to, but there you go. There's the eigenvector. Okay, sure, yeah. So I took this system, right? This augmented matrix, and I rewrote it as a linear system. Right? I mean, Jeremiah, in all fairness, this is a 2x2 example, right? So it's not too bad. It gets a little bit, the problem gets worse is when you get to 3x3 case, even just finding the characteristic polynomial can be hard because you have to take the determinant of a 3x3 matrix, right? And then it gets worse in 4x4 for the same reason. But you're right, it's not too bad. I think once you kind of get into the habit of doing this, it's not too terrible. And then what are you doing to set to t? So remember, when you're trying to find the homogeneous solutions, right? We know that this system has infinitely many solutions because it has 2 variables, but it only has rank 1, right? So because it has rank 1, all of the columns that don't have a leading 1 in it will be your parameters. So Jack, that's what I'm doing when I say let x2 be a parameter, right? When I say let x2 be equal to t. Yeah, I'm trying to remember if there are any 2x2 matrices on the test. I don't think so. Yeah, I don't think there are any. So Curdy, are you okay? Like the explanation of x1 and x2 there is fine, and you got the eigenvector. Okay, yeah, no problem. Jack, I don't know if not Jack, Brandon, I don't know if I'm going to get to finance today. We can do it on Thursday for sure, though. Yeah, and like I'm happy to talk about it. That question can be a little bit tricky, though, so it wouldn't hurt if we did some poll questions first, and then maybe it'll clear itself up as well. Like I'm hoping that's true. Alternatively, ask it on Piazza, and I'll be happy to, when I get a second, try and answer it there. Okay, so yeah, throw it on Piazza as well, and we'll do our best. Yeah, and everyone that's gonna take care of it today. So hopefully that helped you out. Study hard for I can row reduce by hand. Can that be one of the questions on the quiz? Well, Dodd, unfortunately, because the computers can also row reduce and actually give you the steps. We don't want people to be able to do that because we said you could use computers. So that would be 100%, a full marks question too. So unfortunately, no, that probably won't be a question. Or it could be something that has a variable in it. So you can't just necessarily ask a computer to do it. And then you could row reduce like that. Yeah, that could be a question, right? But yeah, okay, everyone, that's going to take care of me today. If I can book an appointment. Right, okay. Let me take a look at my emails later and I'll make a consideration. I'm pretty packed this week too. But let me look at my schedule and see what it is. But I am also unfortunately like very packed. What I'd recommend though, definitely tutorials, definitely the TAs also have office hours, drop into those as well. Like I said, I'll try and find something in my schedule, but I'm really not certain I'm going to find anything because this week is just, I'm dying. Okay, no problem, Christian, thank you. Yeah, absolutely. Like I said, I'll try and find some time, but I make no promises. All right, everyone, thanks. Have a good Wednesday, and I will see you on Thursday evening. Okay, ciao.